All right. So thank you everybody so much for being here. It's my great pleasure to introduce Aditya Varre, who is at EPFL and working on the spectral bias of two-layer linear networks. And so, yeah, floor is yours.
Thank you, Stefan. Thank you very much for the opportunity to present my work. I'm Aditya. I'm a PhD student with Nicola Flammarion. And today I'm going to talk about joint work with Maria, Lucas, and Nicola. And it is on implicit bias of linear networks, or more specifically, it's on what we call spectral bias of linear networks. Okay. So let's go through what is my agenda for today's talk. So I will very briefly discuss what is an implicit bias of an algorithm, and also discuss a bit on what are the factors influencing this algorithm's implicit bias. Then we will look at a motivating example. We will look at very closely at some empirical evidence on training shallow ReLU networks. And then we will try to characterize these phenomenon for in the case of linear networks. And towards the end of the talk, I will talk about a different paper where we look closely at stochastic gradient descent. And there we talk a bit on what is the role of step size. And this paper is more empirical. And here I will provide some empirical evidence on ReLU networks, deeper networks, and linear networks to see what an implicit bias of SGD with the step size is going to be. Okay. Okay. Let's start with the supervised learning problem. What we have is we have some input and output samples coming from an underlying distribution. And the goal or the learning objective here is to learn a function which maps from your input space to the output space and which will predict well on a future data. And the challenge here is you don't know the underlying distribution. So you learn from from some instances of from some input data you have. So we assume that there is some low complexity ground truth which predicts well. Otherwise, due to no free lunch, you cannot. You cannot expect to solve this problem, or you cannot expect good performance on our future data. So traditionally, how this is solved is you choose a complexity class. It can be some parametric class, it can be neural network, an SVM, or some hypothesis class, and you solve an optimization problem, which is the empirical risk minimization problem, and look for some low complexity solutions, which predicts well on your observed data. So, for example, it can be a regression task where you look for a minimizer of your square loss. And so what classical generalization guarantees tell us is, so it depends upon your complexity or with complexity of your hypothesis class, which can be like a VC dimension or a Rademacher complexity. And it says that the learning guarantees follow this polynomial law or some power law. As your number of samples go, you get some good learning guarantees on your as you have large number of samples, you get some good learning guarantees. Okay, but the problem is these guarantees does not always apply to deep learning. Because particularly how classical learning theory worked was, okay, you restrict your space to low complexity solutions. You either regularize it or you use some external regularization and say that, okay, because of this, the complexity is less and you get some good learning guarantees. But the parametric class or the function class represented by neural networks is large and it does not necessarily have a low complexity. But the thing is, there are some tools which allows you to extract these low complexity solutions. And these tools implicitly does it. And our algorithms, like first order algorithms, primarily like SGD or GD, implicitly does it. And they extract these low complexity solutions. And this is what is called implicit bias of an algorithm. And to give a bit more specific example, consider the problem of linear regression. So you have a linear objective and you have some input variables, and you have output labels. So you solve this linear regression task. And to say that the complexity class is huge, we place ourselves in a over-parameterized linear regression setting, which means that there are many optimizers or many regressors beta which solve this objective. In some sense, they have zero loss. Okay, but if you start your gradient descent or stochastic gradient descent from 0 and run it, it does not converge to any solution, but it converges to a very particular solution which minimizes your L2 norm of your, which minimizes the L2 norm of your weights. So you converge to a solution of all the possible solutions which has the lowest norm. And the algorithm implicitly imposes some complexity control in terms of L2 norm of your predictor or of your regressor here, beta. And this is called implicit regularization. And because the capacity control or the complexity control is implicit and you're not imposing it. It just comes from your initialization and your choice of algorithm. Okay, and this has led to a lot of works and a lot of focus. I mean, this observation has led to a lot of works and a lot of focus on implicit regularization and what are the factors in influencing this implicit regularization, and can we characterize it for models beyond linear regression. And yeah, and one of the, at least for regressions, one of the most one of the models for which you can theoretically capture a lot of phenomenon which are happening in reasonably capture a lot of phenomenon which are happening in deeper networks is diagonal networks. Okay, so basically diagonal networks is like, you can assume it is like a neural network with one hidden layer, and both the weight matrices are diagonals. Both the matrices are both the weight matrices of your network are diagonals, and you have a and you yeah and okay, and for this regression task, if you again run a gradient flow, which is like a continuous approximation of gradient descent or stochastic gradient descent at a very small step size, what you get is like, okay, you take your parameters, you initialize them at a scale, and depending on your initialization scale, you see a range of implicit biases. So for an initialization scale very close to 0, you go to a L1 norm interpolator, and for initialization scale larger, you go to an L2 norm interpolator. Okay, why is this important? For example, assume you're solving a sparse task, or if your ground truth is sparse, and you want a sparse predictor beta which solves your linear regression. In that case, it is good to have an implicit bias towards a min L1 norm interpolator. And here, by just taking a slow initialization scale and running your gradient flow, you're getting such an implicit bias. And this is more from a practical point of view, but from a theoretical point of view, this presents a non-convex model where, just due to non-convex dynamics, it exhibits a lot different implicit biases, and it really allows you to study some phenomenon or capture some phenomenon. Although it's very simple, it still allows you to capture some phenomenon which happens in a much deeper networks or much complex networks. And through this model, a lot of people have studied what are the regularization properties or implicit regularization properties of stochastic noise, of step size, momentum, and various aspects. Okay. And now I also want to just give a brief overview of some past works on implicit regularization. So this started with some seminal works on classification. So if you just take a logistic regression and run gradient descent or stochastic gradient descent, your predictor will be implicitly biased towards an L2 max margin. And this was also extended for beyond linear models to include fully connected linear networks. And here it is shown that if you run gradient descent or stochastic gradient descent, it implicitly aligns your layers of your weight matrices. And again, you get an implicit bias towards an L2 max margin. And there were also works which are characterizing at infinite width limit the implicit bias towards some variational norm. And this can be extended to general homogeneous networks with some restrictions. Okay, and on the regression front, there is a work on matrix factorization, which says that there is a conjecture which says that if you, similar to sparse predictors here, if you do a matrix factorization problem, you have a implicit bias at small initialization towards low nuclear norm solutions. Okay, and similarly, if you, again, for nonlinear ReLU networks, when you're training with gradient flow, and if you initialize at a small scale, you have an implicit bias towards some minimum norm interpolators. Okay, sorry if it was a bit too quick. And now let's slow down a bit and take a motivating example which shows that why these implicit biases might be important, or what does it mean. So for this, I take a shallow ReLU network. So, and what I do is like I take some input data, and you can take the input data from some standard normal distribution, and I generate the labels by a teacher network. So I take the inner product with the teacher network, and I apply the nonlinearity, and I generate my labels. So here you can think of this as like your network has two features, or your labels are generated by two features which are orthogonal to each other. And then what you do is like you train a student network which is much larger, and you want to see if this recovers these neurons, or if it recovers these features, or to which networks this student converges to. Okay, and so the training algorithm here, the loss function here is again a square loss function, and we train with gradient descent, and we choose an initialization such that we initialize all the inner layer, or all the rows of all the entries of the inner layer from a standard Gaussian distribution. However, we control the variance with some with the parameter gamma. Okay, and this I refer to as the scale of initialization, or you can also think of it as a variance of initialization. And the linear layer here, I initialize it to 0. Okay. So let's see. So here, what I'm showing in this graphic is the movement of the neurons when, or the direction of these neurons, or the direction of the weights of these neurons, to be precise, when initialized with a larger scale. So as you can see, the neurons points to many different directions, and the network learned at the later stage corresponds to a random, at least the features, the WIs learned corresponds to random features, and this is called lazy training, as it's not really recovering the ground truth features, or the features U and V. However, if you train the same network at a smaller scale, you can see that these directions collapse to a very few directions, or a very small number of directions, which basically means that your weight vectors are really learning some features, and this is what is called feature learning. And if you just plot the singular values of your weight network at different scales of initialization, as you can see, the matrix is full rank at a large initialization scale, which is basically means that your inner matrix is almost random and did not learn much features. So this is, in both the scenarios, I train to 0 loss. In some sense, you train to a network which completely fits your training data. However, In one case, the matrix is almost quite random. And in other case, it learns two principal directions, which corresponds to your features U and V. Okay, let me just again repeat. So what you do is like you have a teacher network with two neurons, and you train a student network with multiple neurons, and you try to see if it recovers these teacher neurons or not. Okay, and basically the summary is at a small initialization scale. If you initialize your weights at a small scale and run GD or SGD, you recover it, or you almost converge such that your weight matrices either point to the directions U or V or some linear combination of it. Or when the initialization scale is small, when the initialization scale is large, it points to almost random directions, as you can see from the singular value plot here. Okay, so when the initialization is small, you have a low rank bias. And the question is now is, can we capture this theoretically? But here, this question is open even for a linear network. So this is a linear network. I'm training at a larger scale of initialization. And as you can see, all the directions are pointed towards, the directions of the inner layer are pointed towards random directions. However, if I train at a smaller initialization scale, although they are random at initialization, they quickly converge to one relevant direction. I mean, here it's one direction and the completely opposite direction of it. And it is the inner layer here is meaningful. Okay, and this is the main message of the first part of the talk, and to characterize this low rank bias in the weight matrices when training with gradient descent or gradient flow. Okay, and now I'm ready to set the problem up. So here you have so we consider a linear network, and with lots of generality, you can assume that your labels are generated by a linear function. Okay, and the linear network has a linear layer A and the inner matrix layer W. So note that by reparametrizing it like this, you don't gain any representational capacity. In that sense, still the functions it can represent are only linear, but what you gain is like, you gain, still if you train with gradient descent or gradient flow, and you train on the square loss, it is still non-convex in W and A, and still for this non-convex objective, it is a priori not clear even if you converge to zero loss or the minimizer of the loss. I can assume here zero loss because I assume that there is a regressor which generates my labels. Okay, and for this problem, there are two levels of overparameterization. First, I consider the scenario when the output dimension, the dimension of the input is greater than the number of samples I have. So there are many interpolating solutions in the linear space or in the function space. They're such that x beta equal to y. So you can take a vector beta where x beta equal to y, and you can add anything in the kernel of x or kernel of the columns of x, and you does not change your predictions. So there are many interpolating solutions. Similarly, consider any beta, and for any such beta, there are many representations. So take a beta, and then it can be represented in many ways by these matrices W and A. So there are two levels of overparameterization here. The first level is in the function space where you can always add some elements in the kernel of X, and it does not change your predictions. And the next level of overparameterization is in the representation space where even for a certain function, you can have many representations. Okay. And for this, I choose a very particular initialization. So what I do is like I initialize my inner layer W, or my hidden layer, my matrix, my hidden layer W here, or with a orthogonal. The shape of the initialization is an orthogonal matrix with some scale gamma. And the linear layer, I initialize it to 0. And and on these inputs, I run a gradient flow to train this network. Okay. Yeah. So I have a square loss. I initialize my inner layer to an orthogonal matrix with certain scale, and I initialize the linear layer to 0. And here I run a gradient flow. Okay. And now I very briefly discuss some related works on linear networks. Okay. Most of the related works, or most of the works people have studied, they only try to characterize what is the implicit bias in the function space, or in where your predictor, which is W transpose A, after you converge, where this is converging to. And note that, yeah, and here what I try to say is like, okay, still all you're learning is a linear function, so it might be just important what beta is, where your beta is doing. But I say that, okay, it is also important to see where your weight matrices are converging to. It might not make a difference in linear networks, but I think if you are looking at nonlinear networks, it is important to understand the dynamics it induces, and there are some similarity in the dynamics for nonlinear networks, and this is why it is also interesting to look to where you're converging in the representation space. Okay, and most of the works also study only a balanced initialization, or study initialization with some spectrum which is already aligned with your target. Okay. And this is where the work is a bit different from the existing works, where we really look at we at least try to look at to which final weight matrices you're converging to. And we look for more general initialization schemes than a spectral initialization or a balanced initialization. Okay, note that although I say that you are initializing with you're initializing with an orthogonal matrix, if you're initializing with a very if you're considering a network with a very high width, or with very high width on your inner layer, and you're initializing randomly from a Gaussian distribution, your initialization is almost orthogonal. Okay. Yeah. And now I'm ready to state the main result. Okay, now we take this linear network, we trained it with gradient flow with the specific initialization as I shown before, which is orthogonal initialization with the scale gamma. So first, as I told you, a priori, it's also not clear even if you're just converging to zero loss. So we can show that you are converging to the zero loss of the solution. And for any scale of initialization gamma, your beta at infinity is the min L2 norm interpolator. Okay. And coming to the parameters, what we can say is like you converge to the parameters which satisfy this variation inequality. So of all the parameters which you interpolate, your parameters satisfy this variation inequality, which is the sum of norms of your parameters minus a log dead term. So this log death is like a smooth approximation of your rank. And when your gamma is 0, it means that you are converging to a min norm interpolator And this ensures that your rank of your inner matrix is 1. And as you increase your gamma, log det, which is a smooth approximation of your rank, pushes your inner matrix W to larger ranks. Okay. So again, I train with gradient flow and I choose a specific initialization shape. Here, for any scale of initialization, my implicit bias in the function space is always the same, but you are converging to various representations where in some representations you have a very informative low rank matrix, and at some other as a inner layer, and where at other initializations you have an almost random matrix. Okay, and I also want to point out that this the set of these minimizers is not unique. You can always rotate your matrices, but it's still informative, saying it really saying that it distincts the set for different scales of initialization. Okay. Okay, and you can also give what are the singular values of your the inner hidden layer matrix for different scales of initialization. So as you can see here, what happens in this case is, okay, only one direction grows and the other directions stay the same. And here I also plot for a normal, not for this initialization shape I have theoretical results for, but also for a normal Gaussian initialization. And what happens here is like, okay, you only see the growth in one, or your parameters grow in a very particular directions to fit your data. And when your initialization is very low, the other directions doesn't matter. But if your initialization is very high, your matrix resembles an almost random matrix. And as you can see here, for the large scale of initialization, which is represented by dashed lines, at the end of the convergence, again, what I want to say here is like I'm plotting the singular values, but by the end of the convergence, almost you went to zero train loss for all the 3 networks here. But as you see, when you initialize at a higher scale, your matrix towards which you converged at the end has a very high rank and resembles a random structure. However, when you initialize at a smaller scale, your matrix has some rich low rank structure at the end of your training. Okay. Okay. The same you can say for a vector regression. Here, basically, you have instead of last linear layer, which is a vector, you can have a matrix, and you can say that my function now maps from an input space D to an input space K instead of a scalar regression where we were considering earlier with 1. And the results also hold here. And as you can say here, I am plotting the singular values again for K equal to 3. So in some sense, you need a rank 3 matrix at the end. You need at least a rank 3 matrix to fit your training data. And again, at a low initialization scale, you go to a rank 3 matrix, and you see this separation depending upon your scale of initialization. Okay. Okay. It will probably okay. I just give a brief proof sketch. So basically, what happens is like first, what we show is like the weight only evolves in a subspace. In some sense, depending upon your initialization, there is this huge space of space which is perpendicular to your initialization, or you can just take a matrix which projects into your weights into a space perpendicular to the row space of your initialization, and these matrices do not evolve and they stay 0. And Now, what you can do is like you can consider the projection onto this space, onto the row space of P, and uh, you have a particular and you have an invariance of the gradient flow here, which says that your weight matrices are a low rank perturbation of an identity. Okay, and this is one property, and the other property is basically which says that the other property basically says that Z inverse Z2, or like there is a particular quantity which you can track, and this quantity always evolves in the span of your data, and you can use this quantity to derive a variation inequality on your weight matrices, such that in some sense you can construct some potential functions on your weight matrices such that uh, your dynamics satisfy, or towards the end of your convergence, your weight matrices satisfy the KKT conditions corresponding to this variation inequality problem. Okay. Okay. Now I only talked about implicit bias, which is like an asymptotic property in some sense that, okay, we were trying to characterize where you're finally converging to. So for now, till now, we are only trying to say how the matrices look at the end of training. Okay. But sometimes it's also important to see that how you get there, or what we call an anytime implicit bias, to understand how these metrics arrive to the specific structures along the training. And here it exhibits this rich saddle-to-saddle dynamics for the vector regression problem, where you can initialize at a very small scale. And note that note that 0 is a saddle point for these dynamics, because both the gradients vanish at 0 at the due to the reparameterization. So when you initialize at a very small scale, it takes a lot of time to escape 0, which is the first saddle. Then it goes to a rank 1 structure, and it also spends a lot of time to escape this rank 1 structure. And finally, it goes to a rank 2 structure. And again, it's a saddle, and it tries to escape this saddle and converges to 0 training loss. Okay, and you see this saddle-to-saddle behavior on your loss. On your loss plots. And again, if you look at your singular values, you can clearly see that you shoot each singular value at each of the saddle, saying, okay, at the second saddle, I learn a rank 2 structure, and at the first saddle, I learn a rank 1 structure. Okay, but again, this we only characterize with some restrictions on our data, or for almost orthogonal data, and it is open to give this characterization for any general data matrix. Okay.
So just one question. So why is there a separation in the dynamics? Any intuition why that particularly happens? Like, I mean,
so the intuition is okay. So the time where this singular value shoots depends upon the singular value of your target. So in some sense, for at least for the orthogonal data, you can really tell at what or asymptotically at a 0 initialization scale, you can give at what time this singular value shoots. Okay, and it really depends upon, say, you're converging to some target which has a singular value sigma 0 star, sigma 1 star, and sigma 3 star, and these times depend really on the sigma 0 star, sigma 1 star, and sigma 3 star. And just to give a make it visually pleasing, what I did is I choose such that the sigma 0 star and sigma 1 star and sigma 3 star are a bit different from each other, so that it shoots at different times.
okay, but
Is it clear?
yeah, so it's like the higher ones are learned first and the later ones are learned later, and the smaller sigmas.
Yes,
Is it?
exactly. It's inverse to the
Okay.
Well, okay. right now what I said is like, okay, low initializations are better, or initializations at a smaller scale are better because it learns some meaningful structures. However, when we are doing some practical training, we are not really initializing at a lower scale. And it is also a bit impractical to initialize at a lower scale because it drastically slows down your training progress. And this is like a trade-off where you have on your optimization and the trade-off you have on your optimization and your generalization or on your implicit bias. Okay, so now we try to argue a bit, saying that, okay, practical networks might be working well because of the stochastic noise in training. And okay, a closer look at stochastic gradient descent. So now you have your inputs and your labels, and say now you consider a square loss on a network parameterized by theta. Okay, and in stochastic descent at time t+1, what you do is like you take a gradient with respect to you sample an input from your data. Here I'm taking batch size 1, and you take the gradient of this data point, and you update your parameters here with a step size eta along the negative direction of your gradient. Okay, so just to say, this is again joint work with both Lucas and Nicola and Maxime, and this is on SGD, and we argue why SGD with large step sizes learn some sparse features. Okay, and I will try to explain what I mean by this. Okay, again, go to the motivating example, which is a training ReLU network. Training ReLU network. Here you have 3 neurons, or you have 3 teacher neurons. Okay, and you train your network on with SGD with a step size eta of 1.3, and you train a stacker network with a step size a bit larger than 1.3. And what you do is after 50% of your iterations, you decay your step sizes. Again, at the end of your training, both the networks have a 0 training loss. But as you can see here, when you're training with a small step size, again, the network at the end resembles a bit of a random network, and your features or your weights in the feature layer are not meaningful. So here the dots represents what are your weights before training and what are your weights after training. And some of the weights only barely move, which means that you are in a lazy regime. And they're not really forgetting their bad initialization conditions. Okay. However, when you train with it's the same initialization. However, when you train with the larger step size, you see a rank collapse in your inner layers, where your inner layers align towards the 3 way directions of your teacher network. Okay, and this is what is of rich regime, where all your where the weights in your layer are meaningful and aligned with your teacher. Okay, and as earlier what we have said is like, okay, initialization depends on your initialization. Either you operate in the lazy regime or in the rich regime. Here we are contrasting that for the case of SGD, saying, okay, SGD, depending on what step size you take, you either operate in a lazy regime or in a rich regime. And this step size also allows you to transition between these regimes. Okay. A more visual character or a more visual explanation of what is happening here is, so, okay, take now I'm plotting a loss slice of a diagonal network here, but it's not important. Here, what happens is like, say you're running gradient flow or gradient descent. So you're converging towards a solution where your desired solution is somewhere along here. But what happens when you do SCD with large step sizes is like, the step size does not allow you to converge. So it keeps oscillating along the loss manifold, and the noise drives you towards a good direction. And this is the intuition I want or you to have in mind. And I will present some evidence saying like this is what it happens. And yeah, okay. So again, the question or the observations here is like the noise is driving you towards some specific structures. What are the properties of these what are the properties of these structures, or what are the properties of the solutions uh, where you are converging to, and what is the role of the step size? Okay, and the main key observation is whenever your loss stabilizes, in the sense that you don't quickly converge to, your loss doesn't quickly converge to zero, you learn meaningful structures. So for the ReLU example, where you are converging to a good solution with a large step size, basically what happens is like your loss does not quickly converge. It keeps oscillating till some point, and when you decay, it converges to zero loss. And at the end of the training, the network you obtain has a better structure, in some sense, a low rank in your inner layers. Okay, and this can be seen a bit in a ReLU network in one-dimensional case. Say you have these regression points where your data is in one dimension and your output is also in one dimension. And if you're training with a small step size where your loss is converging very quickly, you fit these points, but you converge to a network which has many bumps or which has many bumps. However, if you let your loss not converge too quickly by controlling your step size and then decay it at some point, then you converge to a good solution which completely interpolates your data, but now has again completely interpolates your data, but now has a fewer bumps or nicer structure. Okay, and yeah, and this is true along on multiple architectures. For example, you can take a diagonal linear network, and here I try to capture the rank of your NTK matrix, and as you can see here, by increasing the step size, whenever the loss does not decrease too quickly, you go to much lower rank of your feature matrix. Okay, and this is also true for a multi-layer ReLU network. Well, and the same thing also happens for deeper networks. In some sense, whenever you see a loss stabilization, or you see a case when your loss does not converge too quickly, you see sparser structures. So here we define a feature sparsity coefficient. It's a curated metric to intuitively capture the rank of your feature matrix or the rank of your NTK matrix. And as you can see, as you train with large step sizes, your network sparsifies and sparsifies. The longer you train with your large step sizes, the sparser network you go to, and it also correlates with the generalization, where you train the sparser network generalizes better. Okay, and these are experiments on with DenseNet on CFAR and on TinyImageNet, both confirming our observations or our intuitions on smaller models. Okay. Well, you can take a theoretical approach to study this loss stabilization. So what you can do is like you can approximate your SGD by GD plus some noise. The noise, what is very important here is like the noise has a particular scale. And as demonstrated in some works before, the scale of your noise in over-parameterized networks or modern machine or modern image classification tasks, the noise scale is proportional to your loss. And when your loss converges very quickly, you don't get this good benefit of noise just because your scale is vanishing very quickly. And it also has a particular shape, which is where its covariance matches with the covariance of NTK. Okay. And this brings us back to, or this connects with some works on label noise, where label noise is basically saying, I take a IID at every iteration, I sample some Gaussian noise and I add it to my labels, and I take a gradient on these new labels. So what is the good property of this label noise is that it matches the first two moments of, okay, it matches at least the shape of the noise covariance, And when the loss is constant, which is due to the loss stabilization and choice of the large step size, what you can say is like, you can say that my large step size SGD is almost equivalent to label noise SGD with some constant intensity noise. And what does this gives us is like, it gives us another tool to study large step size, because large step size it's a discrete dynamics and it's very hard to study. However, label noise is a bit easier thing to study, and you can also approximate it by continuous time using an SDE. And there are some nice works which study this label noise SGD. So what we do is like, we say that, okay, large step size SGD has a label noise like behavior. So if you want to really capture what large step size SGD is doing, you can instead study label noise SGD, which is easier to study, and say something something meaningful on what implicit bias noise is giving. And okay, here I try and again, coming back to the linear network, here I again try and network initialized at a large scale, but now instead of gradient flow, I'm trying with a label noise stochastic gradient descent. And as you can see, it still recovers the low rank structure. Even if I start at a large scale of initialization. Okay. And this is again experimentally, this is an SDE or an SDE approximation of a label noise gradient descent. And here, when I run it on some synthetic data, you can see the difference between gradient descent and label noise gradient descent, where label gradient descent, okay, it only grows in a small subspace, but it does not kill the other subspace which are of non-relevant directions. However, if you run label noise gradient descent, it kills the subspace on it kills this subspace, and you get a rank 1 structure towards the end. Okay. Okay. I will not, in the interest of time, I will not dwell into the theoretical result, but I can again show you how the evolution of singular values look, say for a network with 2 rows, or like okay. So basically what happens here is like, you can think of it as 2 singular values. One singular value is growing and other singular value is decaying. Okay. Yeah. And you get a low rank structure because of this. Okay. Very technically speaking, what happens is it induces a Brownian motion on your singular values, and due to Brownian motion, it introduces a geometric Brownian motion on your singular values, and one singular values has a larger has a positive drift, another has a negative drift, and basically that's how it induces the low rank structure. That's how this particular noise shape induces a low rank structure. Okay. Yeah, and some interesting extensions of this work could be to understand the discrete time dynamics, or discrete time dynamics of both gradient descent and stochastic gradient descent. And as you can see from the plot here, you only get low rank structures when you train stochastic gradient descent with large step sizes. Gradient descent with large step sizes also induces some oscillations, but these oscillations again restrict to the small subspace, but it does not really kill the non-relevant directions you want to kill. Okay, this is one interesting direction to study the discrete time dynamics. I think it is possible to study with some restrictive assumptions on your data, and and the next interesting question is to, again, as I told you, the motivating example is more nonlinear networks. This is why we look at the weight matrices. So again, to characterize this behavior for nonlinear dynamics, to characterize at least the saddle to saddle behavior, where and this is partially done by some people in our group with some particular assumptions on your data matrix, for example, for orthogonal data. But it is interesting to give a general characterization for this for a regression task. Okay, just to recap what we have done so far. Okay, very quickly, we saw what does an implicit bias of an algorithm means and what is its relevance. And we discussed two factors influencing such an implicit bias. One could be the scale of initialization, and the other is the presence of stochastic noise, or the amount of stochastic noise you have in your gradient-based training. And this is revealed the role of the step size. And first, we presented some rigorous characterization of where your networks are converging in the case of linear networks. And towards the end, we saw more an empirical treatment of in the case of stochastic gradient descent. Okay. Thank you. And this and